Comparison of the ionic radii with corresponding atomic radii. First of all, what are ions? Ions are the species or atoms or group of atoms which carries positive or negative charge. The atoms which carries positive charge are called cations and atoms which carries negative charge are called anions. Here we will compare the radius of cation with radius of atom. The radius of cation is always smaller than that of its parent atom. Let us illustrate this with an example. For example, this is sodium. Its electronic configuration is 1s2, 2s2, 2p6, 3s1. It means in its last shell there is only one electron, that is in third shell. When it loses its last electron from the outermost shell, it becomes Na positive, means sodium cation, and its electronic configuration changes to 1s2, 2s2, 2p6, means stable configuration. Here the sodium atom loses its one electron to become Na positive. In atom there are only 11 electrons and in cation there are 10 electrons. But the nuclear charge for sodium is plus 11 and also for the sodium cation it is plus 11. It means it remains same, means number of protons remains same for sodium atom as well as for sodium cation, but the number of electrons reduced from 11 to 10, and this results in the decrease in number of shells and increase in effective nuclear charge. Due to this increase in effective nuclear charge, the nucleus attraction towards the outermost electrons becomes more, and they are tightly held, strongly held towards the nucleus. This is the reason for the reduction of the cationic radius. Next is comparison of the ionic radii with corresponding atomic radii. In this, radius of the anion is always larger than that of its parent atom. In chlorine, there are 17 electrons and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. It means it has tendency to gain one electron, and if it gain one electron it becomes Cl negative, means chloride ion or anion, and its configuration changes to 1s2, 2s2, 2p6, 3s2, 3p6, means stable configuration. Chlorine atom contains 17 electrons, but the anion contains 18 electrons due to the gain of one electron. And the nuclear charge remains the same for atom to anion, that is plus 17. This results in electronic repulsions, means electron-electron repulsion increases due to addition of the incoming electron, and the effective nuclear charge decreases. It means size increases. Next is isoelectronic ions. Isoelectronic ions are those species which are neutral or ionic and have same number of electrons but different number of protons or nuclear charge. For example, aluminium 3 positive, magnesium 2 positive, Na positive, neon F negative, O2 negative and 3 negative. All these contain same number of electrons, that is 10, but different number of protons, that is plus 13, plus 12, that is nuclear charge, plus 11, plus 10, plus 9, plus 8 and plus 7. Next is the variation of ionic size among the isoelectronic ions. As the charge on the atom decreases, the ionic size increases. Means from aluminium 3 positive to N3 negative, the ionic size increases due to decrease in the charge on the atom. Next is ionization enthalpy. Ionization enthalpy is the amount of energy required to remove the loosely bound electron from an isolated neutral gaseous atom or molecule. Here in this picture, this is the loosely bound electron, means away from the nuclear attraction. When we remove this electron, we need some energy to knock out this electron, and this energy is called ionization energy. Successive ionization enthalpies. Successive ionization enthalpies means energy required to remove the electrons in steps, means first electron, then second electron, then third electron from the isolated gaseous atom, and the energy required in different steps is called successive ionization enthalpies. And the third ionization enthalpy is always greater than second ionization enthalpy, and it is always greater than first ionization enthalpy. Let us illustrate this with an example. Here, aluminium in gaseous state, when it loses one electron, it becomes aluminium positive, and its ionization enthalpy is 577 kilojoules per mole. Electronic configuration of aluminium here is 1s2, 2s2, 2p6, 3s2, 3p1. When it loses one electron from the 3p orbital, it becomes 1s2, 2s2, 2p6, 3s2, means stable configuration. And when we remove second electron from the aluminium ion, that is Al positive, it becomes Al2 positive, and configuration changes from 1s2, 2s2, 2p6, 3s2 to 1s2, 2s2, 2p6, 3s1, and its ionization energy increases, which is equal to 1795 kilojoules per mole. This is because the s electrons are more close to the nucleus than p electrons, and when we remove third electron from the aluminium 2 positive, it requires more energy than second electron when we remove the second electron. And here the electronic configuration for aluminium 2 positive is 1s2, 2s2, 2p6, 3s1, and changes to 1s2, 2s2, 2p6 for aluminium 3 positive, and its ionization energy increases, that is equal to 2758 kilojoules per mole. And these three energies, in which 3 electrons are removed one by one, are called successive ionization enthalpies. Next, factors governing ionization enthalpies. First is nuclear charge. As the effective nuclear charge increases, ionization enthalpy also increases, because electrons come closer to the nucleus and they are tightly held by the nucleus, and more energy is required to remove the electrons from the outermost shell. Next is the atomic size. As the atomic size increases, ionization enthalpy also increases. When the atomic size increases, ionization enthalpy decreases. This is due to the fact that when the electrons are close to the nucleus, they are tightly held and difficult to remove the electron, and we require more energy. When the electrons are far away from the nuclear attraction, they require less energy and their ionization enthalpy decreases. Screening effect of inner electrons. Inner electrons make a shield to block the nuclear attraction from so that it cannot reach towards the outermost electrons, and this effect is called screening effect. Here the S electrons have more screening effect than P, D and F electrons because S electrons are spherical in shape. They completely block the nuclear attraction and it cannot reach to the outermost electrons, and it means it is far away from the nucleus and we require low energy ionization enthalpy to remove from the outermost shell. But in case of P, D and F electrons, they have some empty spaces in between and the nuclear attraction reaches to the outermost electrons, and hence we require more energy to knock out the electron from the outermost shell. Next is the effect of arrangement of electrons, that is effect of exactly half-filled or completely filled orbitals. If an atom has exactly half-filled or completely filled orbitals, it means it is stable, and due to stable configuration, it requires more energy to remove its electron from the outermost shell. Variation of ionization enthalpy in periodic table. Ionization enthalpy increases along the period. This is due to the increase in effective nuclear charge and decrease in atomic radius. As the effective nuclear charge increases, it means the outermost electrons are more strongly held by the nucleus, and thereby their atomic radius decreases, and we require more energy to remove the electron from the outermost shell. We move from top to bottom in a group, ionization enthalpy decreases. This is due to the increasing atomic radius or atomic size, and atomic size is increased due to the addition of new shell, and the electrons are far away from the nuclear attraction, and we require less energy to remove the electron from the outermost shell, and hence the ionization enthalpy decreases down the group.